Welcome everyone to John J. McCarthy Observatory's virtual Second Saturday Stars for February 2021. Tonight, we have a program filled with four individual small sessions. The first one is the first of a hopefully recurring session just for kids. Cecilia Dietrich is going to give out of this world words. Then Mark Polanski will show us his winter night sky favorites. Bill Cloutier will give an update on the mission to Mars. And then I'll be giving a quick introduction to telescope basics. And this is part one on refractors. At the end of the program, we will have a period set aside for questions and answers. While you're watching the program, if you do have any questions, please use the chat on the Facebook or YouTube functions. And we have someone monitoring who will ask the presenter. So now to get us started, Cecilia is going to take over and tell us about out of this world words.
Good evening and welcome to Out of This World Words. My name is Cecilia Dietrich and I'm a science teacher at the Thurgood Marshall Middle School in Lynn, Massachusetts, that's near Boston. Some of my students are here tonight, I think. Hi. If you're here, if you're one of my students, go ahead and write in the chat and say hello. This will be an interactive program tonight. I hope you'll all be brave enough to share your ideas with me in the live chat. So whenever you see this blue thought bubble, that's your cue to respond and write something in the live chat. And my friend Bob, he'll be reading some of your responses aloud. Hi, Bob. The first thing I'd like you to think about tonight is, what do you like to look at in the sky? Go ahead and write some of your ideas, some of your thoughts, write your response in the live chat, and we'll revisit this question a little bit later this evening. Tonight, we will explore two words that describe how things move in space. Take a look at this animation. What comes to mind when you see this? Go ahead and list some words in that or ideas about this animation in the chat about like what it makes you think about. Our first movement word tonight is rotate, which means to turn on an axis. Can you see me in the little box just to the right of my slides there? Look at how I'm moving my finger in a very small circle. Try that yourself and repeat the word rotate several times. This will help your brain associate the movement with the word, and it'll help you remember it a little bit better. Some other words that are similar to rotate are rotation and spin. When you hear any of these words, they usually mean the same thing when the topic is space science. Here's a way to help you remember what rotate is about. Listen for the long A sound in rotate and day. 1 Earth rotation equals 1 day and night. So what rotates? Moons, planets, stars, galaxies, they all rotate on their axis. Let's revisit this question. There's still time to share your ideas in the live chat. Bob, are there any responses written in the live chat to this question?
No,
Not yet? Okay. Oh, I do see someone who likes to look at rocket ships.
rocket ships. And the young lady that I know loved to observe the moon, slightly different every
Okay.
night, always beautiful.
All right, these are good things. Okay. We're getting some good responses. I do appreciate that, everyone.
The stars.
Oh, the stars. I've got to add that one to it too. All of these things have something in common. They move in space. Now let's think about this animation. Remember, I'm not asking for the definition. I'm just looking for you to make some associations. So if you have any thoughts or ideas about this animation, go ahead and write them in the chat. And this brings us to our second movement word, which is revolve. To move in a circular motion around something. Can you see how I'm moving my arm in a big circle around my hand? Try that yourself and say the word revolve while you're doing it. This is an example of revolve. Some other words that mean the same or similar to revolve are revolution and orbit. Again, they generally mean the same thing in the space science context. And here's a memory aid to help you remember this word. Remember that revolve has more letters than rotate, and it's usually associated with a longer time frame and larger movements in space than rotate. For example, one revolution of Earth around the sun equals 1 year. And here are some examples of things that revolve. Moons revolve around their planets. Planets, asteroids, and comets all revolve around their sun. And the solar system on the whole is revolving around its central sun. So before I say good night, here's one last thing to get you thinking more about these words in space. The moon always has one face towards the Earth, and you're familiar with this face because you've been looking at it your whole life. Many people think that the moon does not rotate, but that's not true. The moon does rotate as it's revolving around Earth. Can you explain why the moon always shows the same face towards Earth? Try to model this phenomenon with two friends or family members until it makes sense to you. One of you can be the sun, standing in the center. One can be the Earth, rotating on its axis while revolving around the sun. And one person can be the moon, also rotating while revolving around the Earth, which is revolving around the sun. See if you can make this model work so that the Earth can always see the same face of the moon. And this is really fun to do at night with flashlights. So thank you so much for exploring these two movement words with me tonight. I really hope this has been helpful to understanding these words better because they really are very important space science words to know. Thank you.
Another entry of liking to find the International Space Station.
Ooh, that's a good one.
That's a good way to end this.
Absolutely. All right. I'll just I'm not going to be able to put it on the slide at the moment here, but thank you. That's a great one to know about. Thanks everyone for participating. I appreciate it.
Thank you, Cecilia. If you have any questions for Cecilia, you can pop them in the chat at any time and she'll answer them at the end of the presentation. Now we're going to turn to Mark Polanski, and he's going to show us his winter night sky favorites.
Thank you, John. Let me start sharing my screen here. Okay. Good evening, everyone. I am Mark Polanski, and tonight I'm going to show you 3 things to look for in the winter night sky that will be visible for the next few weeks. With the observatory closed to the public due to the pandemic, we know one of the things people miss the most is the opportunity to look through the various telescopes and see things in person. While this won't be quite the same experience as seeing the light from distant objects with your own eyes, it will hopefully give you an idea of what you could expect to see when we do reopen, or maybe through your own telescopes or binoculars at home. Here's a general overview of the sky right now, right about this time of night, facing south. Tonight, I'm going to focus on 3 objects that can be found without telescopes or binoculars, and show you what they might look like if you could look through a telescope, along with some pictures of what a camera could see of the same object. The 3 objects we'll take a look at are M45, better known as the Pleiades star cluster, M42, the Great Orion Nebula, and the planet Mars, which we'll hear more about from Bill a bit later on tonight. We'll start with the Pleiades, also known as the Seven Sisters or Subaru in Japanese. This is a great example of an open cluster, a group of stars that were formed at roughly the same time and are loosely held together by each other's gravity. The stars in this cluster look like a miniature version of the Big Dipper constellation and stand out for being a tight-knit group of stars that can be seen even with some light pollution. They're also fairly easy to spot when you're looking straight up, facing south at about 7 o'clock in the evening. This is what the Pleiades might look like through the Takahashi refractor telescope at the McCarthy Observatory. These stars are an average of 400 light years away from Earth, which means it takes about 400 years for the light produced in the stars to reach us. That's one of the most special things about seeing distant objects in space. We're really looking back in time by looking at these objects. What we're seeing is what the Pleiades looked like in the 17th century. It's also a relatively big object in terms of how much of the sky it takes up. If you can picture how big the full moon is in the sky, the Pleiades are about as wide as 3.5 full moons side by side. The big limitation we have as humans is that our eyes react to light in real time. This means as soon as light enters our eyes, signals are sent to our brain right away to let us know what we're looking at. Think of a faucet in a sink. Our eyes are like a drain, and the light is water coming out of the faucet. If the drain is open, the water flows right down the drain without really stopping. Our eyes do not have the ability to plug that drain and allow the light to fill up the sink. Fortunately, cameras can. A camera can collect light on its sensor for much longer than our eyes can. This lets the camera see much more of the faint or dim details of distant objects, especially when used with a telescope. This picture is about 60 seconds worth of light collected by a camera. You can see much more of the faint, wispy details between and around the stars than you could through the eyepiece. And there are far more stars, and they're much brighter in the background. This particular camera is black and white. It doesn't really see color, so I need to use filters to separate the colors so I can identify what it might really look like. When I combine all the filtered light, it looks something like this. The blue glow around the stars is from dust and gas, lit up by the brightest stars in the middle of the cluster. Here's a side-by-side view of what you might see with your eyes versus what the camera can see by collecting more light over time. With your eyes, the brighter stars and only some of the dust and gas are visible. The camera can see even more of the structure and some of the less illuminated parts, and even some subtle color differences between the blue and the grayish or reddish towards the bottom. The next object we'll look at is the Great Orion Nebula. The constellation Orion is relatively well known for the 3 stars in a row that make up the belt, making it fairly easy to find when looking southeast early in the evening. There are a wealth of objects to see hidden within the constellation, but the only one visible by eye is the Orion Nebula. You'll need fairly dark skies away from street or house lights to find this one. Look for the 3 stars of Orion's belt in the southeast sky around 7 o'clock. Just below the 3 stars, you may see a small fuzzy looking patch with what look like tiny bright stars in the middle. That fuzzy patch is the nebula. Just like with the Pleiades, we'll start with an approximate eyepiece view. This is roughly what you would see if you were looking at the Orion Nebula through the 16-inch telescope at the McCarthy Observatory. The Orion Nebula is about 1,350 light years away, so this time we're looking even further into the past. It's about the width of 2 full moons in the sky. The 4 brighter stars just to the right of center are part of a structure known as the trapezium. There are actually 6 stars in the trapezium. 2 of the stars are smaller and can blend in with the larger stars, and it takes very clear skies and very stable seeing conditions with steady winds to be able to see all 6 of those stars separately. It's a very difficult thing to capture. Just like with the Pleiades, there's more to Orion than meets the eye. The nebula is a vast star nursery made up of huge amounts of gas waiting to form new stars and new planetary systems. The gases are energized by the stars in the trapezium, causing them to glow and light up the surrounding material. Once again, the camera is able to collect more light and show us some of the hidden details of the nebula you might miss with your eyes. And when imaged through color filters, we get a better idea of the different kinds of material that make up the nebula. Different gases produce different colors of light when energized by the stars within. Reds and pinks generally come from hydrogen, while blues and greens come from oxygen. It's easy to think of these things as two-dimensional, mostly because of our point of view being so far away. They just look like flat pictures. In reality, they're very complex, three-dimensional shapes that only look the way they do because of where Earth happens to sit within our solar system and where our solar system happens to sit within our galaxy. For instance, in this image, the darker brown areas are vast collections of dust that are not necessarily mixed in with the colorful gases, but rather in front of them. The brown material is in the foreground, the blue and gray are in the middle, and the reds and pinks are in the background. As you can kind of see, it has sort of a layered texture to it. Here's a much wider view of the entire constellation of Orion. The star Betelgeuse is the orange star towards the top, Rigel is the white star in the bottom right, and the 3 stars of the belt are just to the right of center. The Orion Nebula is the white and pink patch just below the belt. Also visible are the Rosette Nebula in the top left corner, and the Flame and the Horse Nebula in the center, or Horsehead Nebula, and Barnard's Loop, which is a large red C shape in the center made up of hydrogen gas. Last but not least is Mars. The red planet should be visible even in fairly light polluted skies. Look almost straight up while facing south around 7 o'clock in the evening, and you should see an orange dot not that far from the Pleiades star cluster. This time of year, Mars isn't the most exciting thing to look at through a telescope. Generally, it'll look like a bright orange star. At high magnification in very good conditions, you may see some dark patches on the surface, but the best time to really see the details, like the polar ice caps, is when the planet is near opposition, or when Mars and Earth pass closest to each other as they both orbit the sun. Here's what I was able to capture with a camera last year in late September, about a week before opposition. The main benefit of using a camera with a telescope is the ability to collect more light from distant, faint objects. But because planets are so close compared to nebula and galaxies, the sun does a pretty good job of providing enough light that we don't need to collect light for very long at all. Instead, we can capture the light very, very quickly using video. By recording a video at 30 frames per second, it's basically the same as taking 30 pictures every second. If I record a 30-second video at 30 frames per second, I now have 900 pictures of Mars. That may seem like a lot, but there's a problem. This pesky little thing called the atmosphere. It's great for providing air for us to breathe, but it's terrible for taking pictures of things in space. The air and wind in the atmosphere make objects in space look like they're underwater with wobbling and shimmering. When you look up at the stars and they seem to twinkle, that twinkling is from unstable air in the upper atmosphere. Most of the time, this turbulence is random. There are brief moments of calm and tranquility where the details of a planet can shine through and be seen without distortion. If I'm lucky, out of those 900 pictures of the planet, maybe 50 or so will have those clear moments. I can then take those 50 good pictures and combine them together to create a best of composite image, showing off the details of the planet with as little interference from the atmosphere as possible. So thank you, and that's what's visible in the winter sky.
Thank you, Mark. Now we'll move on to Bill, who will give us an update on the Mars missions. You're muted, Bill.
Okay. Well, thank you, Mark. Spectacular picture. I'm going to talk a little bit about Mars tonight because that's what's in the news. It's been a very exciting week at Mars. Start off with a little traffic and weather. The weather on Mars varies quite a bit, as you can see. At Gale Crater, we have a rover right now, and it has a weather station on that rover. And it's reporting a high temperature of 0 degrees Fahrenheit and a nighttime low of 99 below zero. That's been pretty consistent all week. We did get up to about 28 degrees one day. Again, it's early autumn on Mars, so the temperatures are starting to fall. But the difference between the high and the low is because the air on Mars is so thin, so it doesn't retain the heat from the day. As far as traffic, we've had a very busy week. The United Arab Emirates had launched a probe to Mars. It arrived on Tuesday morning. It was followed on Wednesday by China's spacecraft, which consists of an orbiter, a lander, and a rover. And then next week, on Thursday, the US spacecraft called Mars 2020 arrives in the afternoon. If you want to follow along on the mission, again, this will be Thursday afternoon. NASA will start live broadcasting around 2:15. Then you can always go to the mission website and get the details, and then go onto NASA TV to see what kind of coverage and news conferences and other programs of interest that they will have that day. It'll be a full day of informative broadcasts. So this is the spacecraft, the Mars 2020 spacecraft. There's 5 basic components. The top ring section there is called the cruise stage. This is the piece of the spacecraft that has provided all the power and all the instruments to get the spacecraft from Earth to Mars. A total of 300 million miles. It took them 7 months, and they arrived next week. The middle conical section is actually 3 pieces. The outside is called the back shell, and inside that component is the descent stage, and then the rover, which you can see tucked up in the bottom there. And at the very bottom of the screen is the heat shield. This will provide protection to the spacecraft as it falls through the atmosphere. The heat shield will get as warm as 2,400 degrees while keeping the components inside at room temperature. So here you can see the fully assembled spacecraft. This was taken at Kennedy Space Center just prior to being placed on top of the rocket for launch last July. Now, on landing day, things happen very quickly. The spacecraft comes in very hot, about 12,000 miles an hour, and about 10 minutes before hitting the top of the Martian atmosphere, the cruise stage separates. From that time, when the spacecraft hits the top of the atmosphere, to the time the rover wheels hit the dirt is less than 7 minutes. It's called the 7 minutes of terror because everything is happening 127 million miles away. It's all automated, and all the folks on Earth can do is sit and wait. And to complicate things, there's an 11-minute delay because of the distance between the two planets. This is similar to how we landed the Curiosity rover back in 2012, except this mission has some new technologies. One of the technologies that is going to be used on this mission is called range trigger. It's being used to open the parachute. This parachute is over 70 feet in diameter. It's being opened at almost 1,000 miles an hour, which is very tricky to do without ripping to shreds. And this new technology will be used to pinpoint the opening so that we have a precise landing. The other technology we're using is called terrain relative navigation. And this will be used to locate the safest landing spot on Mars. Through cameras and other software, the spacecraft will be comparing the landing area with maps it has stored on board. And if it senses that the spacecraft is going to land somewhere that's hazardous, it has the ability to adjust its descent. And here you can see the descent stage, which has 8 rocket motors, and then the rover down below. Once the descent stage gets close enough to the ground, about 70 feet, it'll lower the rover down on cables to the ground. Once the rover's wheels sense that they're sitting on the ground, those cables will be cut and the descent stage will fly off. So, where are we going? We're going to a crater called Jezero Crater that happens to be located on the side of a very large plain in the northern hemisphere of Mars called Isidis Planitia. The crater is about 28 miles across and is now dry and barren, but billions of years ago, it might have contained a lake. At least that's what scientists believe happened over time. And so here's an artist's conception of what it might have looked like billions of years ago. There's actually, they've identified 2 rivers that appear to flow into the lake and one outlet that flows out of the lake. So even though the lake is long gone, it left behind some interesting outcroppings. These are called deltas. You would find something like this at the end of the Mississippi River. It's a large accumulation of sediment, a lot of clay. And the good thing about clay is it tends to preserve things. So this is where the rover is going to explore, this old delta. And it's hoping to find some indications or signs of ancient life in the rock and in the soil around that area. The mission is going to last 1 Martian year at least, and a Martian year is about 2 Earth years. And over that time, the rover will scout around looking for interesting areas to explore. And if it finds something of interest, it has the ability to collect samples, store those samples, and leave them behind for a future mission to pick up. It's also going to demonstrate some new technologies. One of the demonstrations is called MOXIE. Now, MOXIE is an experiment that is going to try to extract oxygen from the Martian atmosphere, which is comprised of carbon dioxide. And why is that important? Because if we ever go to Mars, if humans ever decide to explore or settle Mars in person, being able to create oxygen there saves us from carrying it with us. And it also is very useful for other applications like making rocket fuel. The other technology is Ingenuity. Ingenuity is a helicopter. This is going to be the first helicopter to fly on another planet. So it's a very special helicopter because the air is so thin. But if it works, we'll be able to use helicopters to scout out locations that humans can't get to or find things that are of interest. This is a NASA promo for the mission, and they have this on their mission website along with other simulations. So sit back and watch for a second. So that's just one of the resources at the mission site. There's also interactive things that you can do, including a photo booth that you can put yourself on Mars. There's simulators and lots of information on the actual spacecraft. Lastly, just to follow up with what Mark was talking about earlier, Thursday night, the night we land on Mars, is also an excellent opportunity to get out and see Mars. It'll be right next to the moon that night. So about an hour after sunset, unfortunately the weather doesn't look too good, but you'll be able to see all the objects that Mark was talking about. And while Mars and the moon appear close to each other, in actuality, Mars is 500 times further away. That's a good opportunity to be able to locate Mars by having the moon as a marker. Thank you. Back to you, John.
Thank you, Bill. That was extremely interesting and exciting. Can't wait for that. Now, a little bit closer to home, I'm going to go through a few slides on basics of telescopes. We all miss Second Saturday as much as you do, and through this session, we're going to replicate some of the conversations that we normally have on Second Saturday night, either on the sky deck or under the dome. Hopefully you'll learn a little bit more about the instruments that we use to look at the night sky. So basically there are three parts to a telescope system, even though we like to call it a telescope. The three components, though, all have their individual importance and their needs for the scope. The first one is the optical tube or the telescope. The second is the mount, one of the most important things. That's what holds the telescope steady and points it where we want it to go. And the last item is the eyepiece. Early telescopes had just an optical tube with a second lens that was the eyepiece. But in later generations, we've separated that, and that has a very important purpose in its own right. So what's the purpose of a telescope? It's to collect and focus light. It's a common misconception that it magnifies the light. It doesn't. It just collects a lot of it and focuses it into a smaller area so we can see it better. Various types of lenses and mirrors get arranged and are firmly mounted with respect to each other to create the telescope. There are three primary types of telescopes: a refractor, which is made up of lenses; a reflector, which is constructed out of mirrors; and a catadioptric, or a compound, which uses mostly mirrors, but also has some lens elements also. Tonight, we're going to talk about a refractor telescope. Now, all telescopes, no matter what kind, they have some common characteristics. First, aperture, most important, the size of the objective. That defines how much light it can collect. Second item is the focal length. So that's the distance from the light gathering device to where the focal point is. Third is the focal ratio. And that's simply the focal length divided by the aperture, but it's also referred to as the speed, because the shorter a telescope's focal length, the faster the light will get from the objective to the focus point. And finally, magnification is not really a characteristic of the telescope alone. Magnification is calculated by dividing the eyepiece focal length into the focal length of the telescope. And useful magnification for any telescope is usually around 2 times the aperture if you measure the aperture in millimeters, or 50 times the aperture if you measure it in inches. So when you get that new telescope at Christmas and it's a 60 millimeter aperture telescope, you should be able to see about 120 times magnification, but that's under ideal conditions. Now, getting a little bit deeper into refractors. So again, as I said, lenses are used as the objective of a refractor. On the left-hand side of the picture we have here, that's the aperture, and light enters the aperture and gets focused at the end of the focal length on the right side of the picture. This is the first and most familiar type of telescope. It was invented in 1608 by 3 Dutchmen, opticians. Hans Lippershey is given credit for the invention, but Zacharias Janssen and Jacob Matthias also came up with designs at the same time. There was a famous spat with the patent office, and Lippershey won that. Galileo used a telescope in 1609 after reading about it, and his type of telescope, which is a very simple telescope, is called the Galilean telescope, and it uses just a single objective. But with that, he was able to create an instrument that could magnify things up to 30 times. And he was able to see the 4 moons of Jupiter. He's able to see mountains and craters on the moon, rings of Saturn, and the Milky Way. Revolutionized astronomy at the time. Today, entry-level refractors have 2 lenses at the front, and they're called achromats. By using 2 lenses, that improves the optical quality, because the different colors of different wavelengths of light are aligned and focused at the same point. But it's still not perfect. The highest quality are apochromats, which use 3 or more elements as lenses. And that gets the crispest, most clear pictures. As you get a bit larger with refractors, they become very unwieldy. The largest refractor ever built was a great Yerkes refractor in Wisconsin. That has an aperture of 40 inches. But to house a 40-inch objective, the focal length has to be 42 feet long. This refractor weighs more than 20 tons with its mount. Very hard to use, but revolutionary at the time. That was built in 1893, so it's quite old. Now, when you're looking through a refractor, as I said before, the light comes in through the aperture and reaches a focal point at the end of the focal length. You use an eyepiece to take that light that's been focused at the focal point and make it so that you can see it through your eye. When you look through a refractor, the image is inverted, both upside down and left to right. If you look at the snowman with the top hat and the bottom right of this picture and watch the different color lines, you can see why that happens. The objective lens focuses the light, but then the light keeps traveling on that path until the eyepiece grabs the light and focuses it for your eye. Magnification is one of those characteristics we talked about earlier. And this image shows you how that works. When you use different, same objective, same telescope, but you use different eyepieces, the magnification changes. If you use a long focal length eyepiece, then the image is smaller. If you use a short focal length eyepiece, the image gets more magnified. But as you do that, you lose quality of the image. Contrast goes away. So it's a dimmer image. So on any night, and those of you who visit the observatory, you know that we're always changing the eyepieces we use to match the conditions that we have. Now, at JGMO, we have several refractors. You might recognize the main telescope stack. On the top is a Takahashi refractor. Mark mentioned that earlier. It's one of our primary imaging devices. It's very high quality. I mentioned that higher quality telescopes have 3 or more lenses. That one actually has 4 lenses, 2 in the front and 2 near the rear. Also on the main stack, there is another refractor, which is a simpler doublet refractor. That's a Meade. The Meade is a 5-inch aperture and about a 1,000 millimeter focal length. The Takahashi, which is much shorter, is only a 4-inch aperture and a 500 millimeter focal length. JGM also owns, was very lucky to have it donated to us, a antique refractor that was made by John Benjamin Dancer sometime around 1860. Maybe a few years before, maybe a few years after, we don't know for sure. That happens to be a little over 4 inches, 4¼ inches in aperture, and 61 inches in focal length. It's a very interesting instrument to see. And despite it being 160 years old, the image in the middle of the moon was taken through that. So even 160 years ago, they were creating instruments that were able to do real science and see awesome images of the moon. Okay. The next part of this telescope basic series will be reflectors, then catadioptrics, and finally with mounts in other second Saturdays. Thank you. And now we'll open it up to questions from the audience. There's about a 30-second delay. So we'll just mention that we're hopeful to be able to open up the observatory in the coming months. We will keep you updated through our website and during second Saturday.
I don't see any questions, but we do have a couple of comments. Ben Thompson says, thanks, Mark. Great pictures. Interesting to see the difference between what the eye sees versus what can be captured in a picture. Ben also says, Bill, nice pic from your road trip. Peter Corrigan says, we can't wait for Thursday. Go mission tomorrow. Thanks for all this fun info. And Jane Lambert says, so happy to see this picture. I haven't seen the dancer in person yet. It's beautiful. And nice job, John. Thanks for hosting. Janet Parlato asks, how does cold weather affect large scopes?
Well, cold weather is always better for telescopes. The air is stiller and creates less turbulence that we have to see through. It's interesting, if you visited the observatory, we always have our largest scope, which is a 16-inch aperture scope. We didn't talk about that tonight. And we all have some smaller instruments. I'm normally there with a 4-inch refractor. Mark is there with a 10-inch SCT. Roger's there with another 10-inch SCT. But sometimes the 16-inch does not give us the best image. And that's especially in warm nights where there's a lot of turbulence in the air and there's bad seeing. In the winter, though, it is the best time for us to use the large scope. Now, beyond that, I don't know that I can make any comments on even larger telescopes. Obviously, the mechanical systems in extreme cold get harder to use, but they're usually relatively sturdy. Cold is an astronomer's friend.
Another random note I'll throw in as an imager. You generally want your telescope to be ambient temperature, like you want it to be the temperature it is outside when you're imaging. Aside from the air just being more stable when it's colder, like if you take a telescope from inside and move it outside, you can end up with some thermal turbulence within the telescope. Because if your telescope is the temperature of your inside of the house, you bring it to a cold night outside, as the telescope cools, there's going to be a thermal current as the warm air and the cold air displace each other within the telescope tube. That can manifest as a distortion sometimes in an image. It kind of looks like if you've ever opened a window on a cold night and looked up at the moon, you might see it like kind of shimmering, or if you're looking at something through like a campfire, you can see the heat kind of distort things behind it. You kind of get that same effect through telescopes if they're not at ambient temperature.
Excellent comment, Marcus. And especially there's also the thermal mass of the glass itself And that takes time to cool down to ambient also.
Yep. Looks like that'll do it, John.
All right. Well, thank you everyone for joining us. We look forward to seeing you in the March 2nd Saturday. Look for our announcement on our website and in our monthly newsletter. Thanks everyone. Enjoy the weekend and have a good Valentine's Day tomorrow.